So the second talk, or the first real talk of the session, is Dr. Ricardo Otazo. He's going to talk about movienet, fast motion resolved 4D MRI using convolutional networks without data consistency.
Okay. All right. Thank you so much for the introduction. And hello, everyone. Really happy to be here. So these are some financial disclosures. So today we're going to talk about 4D MRI. So these are videos or a series of images, 3D images that are showing movement in some part of the body. In this particular case, this is showing 3D motion in the upper abdomen. So we can see here, you know, the lungs, liver, going down, so pancreas, kidneys. And so the nice thing about having this 4D MRI is that, well, you can actually see these deformations. And also, well, you can reformat in any plane that you want. So one application that we were doing with 4D MRI is just to get better images, free breathing images. And so in this case, we take like a short video and then just pick one frame that is good for the radiologist or the physician. So, and this is analogous to, you know, when, at least in my case, when I'm trying to take a picture of a moving object, for me, it's much better to take a video and then pick one of the frames. It's the same thing here. But the real power of motion imaging or 4D MRI is when we're actually trying to image motion. And this is a need for radiotherapy, where, you know, by having these 4D images, you know, the physicians or the therapists can actually determine the margins for radiation delivery. And, you know, even if they can do MRI before each fraction of the treatment, they can also adapt to the motion of the day. So in this image, I'm showing here like a big lung tumor, also a pancreatic tumor here. And if we actually think about 4D MRI, we can do this in real time. Let me show you something that can be really, really cool for mobile tumors by using this new machine, which is the MR-Linac, which is a combination of MRI scanner and also a linear accelerator. So we can actually do MRI while sending radiation. So with MRI, we can do this 4D imaging with auto-segmentation. We can actually pass this information to the Linac part, 3D position and 3D shape. And let's assume that we can do this in real time. We can actually adapt the radiation treatment to follow motion, okay? All right, so another thing that we can do is that also to get like a very precise dose accumulation map after radiation delivery. All right, so the dream is if we can do real-time imaging. So by that, I mean data acquisition and image reconstruction in, let's say, 300 milliseconds per frame. So the reality is that, well, MRI is not that fast. So what we usually do is we acquire data over multiple motion cycles, and then we sort this data into motion frames or motion states, and then we just reconstruct like one cycle, which is like a one composite cycle. And also the reconstruction here is a high dimensional, so it's slow. So we're still far away from that real-time idea. So with compressed sensing, in particular, this technique, SD-GRASS, and other techniques that follow after that, so we were able to get feasible scan times by using these inherent sparsity or compressibility between motion frames. But the problem is that reconstruction is very long. So we were able to shorten the acquisition, but now the reconstruction became super long because now it's iterative. And also, you know, in each iteration, we're enforcing this data consistency, which in this case is like a 5D data consistency. You need to go to K-space for each time and for each coil, and then compute the residual and then come back to the image domain. So this operation is very, very time consuming. So previous work on deep learning, where they try to unroll these compressed sensing iterations. So now we can actually reduce the reconstruction time since we have fewer layers in the network. but the reconstruction is still not that fast. So we're still using data consistency in each layer. So in this data consistency, particularly important because it's to avoid hallucinations. So that, you know, that then they can also generalize the training and so that the network cannot hallucinate. So in this work, I'm just going to show you some of our new work on this area. We call it movienet. So a fast square motion result for the MRI. So fast acquisition, also fast reconstruction, and trying to move towards real time for the MRI. So we're going to use spatial and convolutional filters, and we're going to remove data consistency. And so we're going to exploit some properties in these 4D images that are going to enable to remove data consistency from the problem and still be able to avoid hallucinations. Okay, so the way that we do 4D MRI is based on SD-GRASP, but now the iterative reconstruction is replaced by a convolutional network. And it goes like this. So we use a stack of stars acquisition. This is like radial in KY, KZ plane. I'm sorry, KY, KX plane, and then Cartesian along KZ. And then we take the first step from SD-GRASP. We detect a motion from here. We sort the data into motion states and then convert it to a 5D image. Since we're going to reduce acquisition time, so these images are going to be aliased since we're sampling below the Nyquist rate. And then this is going to go through a network, and then we'll produce a 4D image. So movienet is using these space-time kernels, no data consistency, no call sensitivity. So the network will do all of that. And here the goal is to make it super fast, that we can do this in a couple of seconds. So this is the architecture that we came out after a few iterations. So it's a standard architecture, UNets. So we're in the input, so we are concatenating motion and coils. And this is going through a network. So for the encoding part, this is we're using residual blocks for encoding and decoding. And so also we split, I mean, here, this part into two sections. So that will gave us more robustness in terms of results. So this part of the network will, you know, encode all the spatial and temporal features. And then the second part, the decoding part, will, you know, remove the aliasing artifacts and also combine the coils. So this is a graphical depiction of what's going on after each block. So here is the way that the network is encoding all of these spatial and temporal features. And then this is all putting together and trying to remove the aliasing artifacts and produce finally a coil combined for the image. All right, now let's try to discuss a little bit this idea of why we can remove actually data consistency from the problem. So I would like to introduce this idea of motion consistency instead of data consistency. So the idea here is that this motion consistency can be applied in the image domain, so we don't need to go to K-space. So when we train the network, so the input are these alias 5D images. So on the reference for training is going to be the iterative SD-GRASP or compressed sensing results. So, and we sort the data in a particular way. So we're going for, let's say, for respiratory motion, we're going from N expiration to N inspiration. And so in the reference for training is also reconstructed in that way. So in other words, like the input motion range is preserved by the network and actually determined by the input. So when we do reconstruction, so also the network will see an input that is also sorted in the same way. And so the motion range that is in the input, that will also be preserved in the output, since the network was trained in that way. So the network was trained to remove aliasing artifacts, but without moving from that motion range. So in other words, so this network is not going to hallucinate. So if your maximum displacement was 2 centimeters, the network will not produce something that is beyond 2 centimeters. Okay. All right. So let me show you now more details about the training. So we use SD grass reconstruction, but acquire more spokes. So we're going to try to accelerate the SD grass acquisition. So we train 2 networks, one at 3 Tesla. These are diagnostic scanners. So for that, we use like 15 patient data sets, and we do a slice by slice training. We train 2 networks. One is going to be for motion compensation, only having 4 motion states. So, and then the input is going to be a super fast acquisition, only 1 minute, 400 radial lines of spokes. And so, and the reference was trained with an SD grass reconstruction, but with 600 spokes. So we're going to go for 400 spokes to 600 spokes, half a minute acceleration. And then the other one is going to be with 10 motion states. This is for motion imaging with a longer acquisition. And then we're also going to train another network for, particularly for the MR-Linac. And this is for radiation therapy applications, and using 10 data sets. And in this case, the network is performing 10 motion states. The input was 600 spokes, like about 3.4 minutes. And the reference was trained with 900 spokes. We took like about 5 minutes, okay? All right, so these are some results. So the first one I'm going to show is, how this network can reconstruct these nice free breathing images. So you see the reconstruction. This is the total reconstruction time, including motion sorting, everything from case space to the final image. It only takes about 2 seconds. So, and this is showing here movienet in the expiration. And this patient has some pathology here in the kidneys, some in the liver. And so you can see an improvement compared to SD grass. So with movienet, we were able to actually reduce the acquisition time to 1 minute. And then the other example is now moving to 4D imaging, like with 10 motion states. And you can see motion, all the structures. So one of the applications of this, at least for the one with 4 motion states, was to reduce the acquisition time and enable free breathing pediatric imaging without anesthesia. In this case, it's showing a case with that 8-year-old kid with cancer. And so this is the traditional scan with 2 minutes with respiratory gating. So this is kind of image quality. Another thing that they also tried was to do 3 averages, no respiratory gating, but with this kind of image quality. And this is movienet. So where we can get much better image quality in only 1 minute of acquisition. So in this case, the patient was able to do it without any anesthesia. So we can also apply it to younger kids. And if we can reduce acquisition time to just a few minutes, we can also reduce anesthesia depth. And this is going to help a lot in these pediatric examinations. All right, let me now move to radiation therapy applications. So this is showing 4D imaging on the MR-Linac. So, and this is a movienet, like a 3.4 minutes and only 2 seconds of reconstruction. This is showing SD grass with a longer acquisition and much longer reconstruction. So basically, there are no differences despite the huge reduction in reconstruction time. But we're not quite there yet in terms of real time. This is still 3 minutes and 2 seconds reconstruction. That's not real time. So in order to be real time, we developed this technique, which is called MRSIGMA, MR signature matching, where, MRI, we need to recognize, MRI is not fast enough to do real time for the imaging. But what we can do is take some advantages from motion. So we can pre-learn a 4D motion dictionary. So let's acquire data. Let's do movienet, right? So let's acquire data for 4 minutes and reconstruct it. And then so we assign like a unique signature to each motion state. And then during the matching part, once we're done with this, we can move to the real-time part. So the real-time part will only do signature data acquisition, which is super fast. And then we'll do matching instead of reconstruction. And that will minimize the latency. So the way that we implemented was, again, using all our toys, radial imaging, deep learning reconstruction. So we acquire data for about 4 minutes. From that, we can get the respiratory motion signal. We can beam it into amplitude ranges. So each amplitude range in each beam is determining the motion signature. So this is passed to movienet, so we can reconstruct the 4D motion dictionary. And then during matching, so once we are done with this, we can move to the real-time part. And then so we repeat the acquisition, but now for each angle, we are gonna get a signature, which is just a projection along the C dimension. And so we're gonna match it. We're gonna find along all of these, the one that's closest to this one, and we're gonna select that state as the output. So that process only takes about 25 milliseconds. So in that case, the total latency, acquisition and reconstruction can be reduced to less than 300 milliseconds, which is good enough to do, to track respiratory motion. Thank you. And then we repeat the same thing for all the next angles. And also after acquiring like a chunk of data here doing real time, we can also get now a new 4D, reconstruction, and that can be used to actually see how well we are doing in terms of tracking of motion imaging here in real time. So this is our implementation on the MR-Linac. So SAT actually developed an implementation. It works all in real time now. So we run the MR-Linac research mode, and then we have a little program that's gonna send the data, each case baseline to this computer, and then we do all the processing here. So the data acquisition takes about 4 minutes, and then data transmission only has an overhead of 5 milliseconds. Then after 2 seconds, we get our 4D dictionary. Then we take a break, and now we could start the real-time part. And so in here, the latency, the total latency, including acquisition and reconstruction, is only 275 milliseconds. And also, since with deep learning, with movienet, now we can also, with deep learning, we can reconstruct these 4D images fast. We can update the dictionary every 10 seconds or so. And with that, we can also account for any problems that, any mismatches between the real-time part and the motion learning part. Okay. Let me show you some examples here. So this is on the MR-Linac, so showing a patient with pancreatic cancer. So these are the contours in reds. This is the tumor, and these are the ongrafts and wrist, the duodenal stomach, which gets really close to the tumor, and you want to avoid sending a lot of radiation when the duodenal stomach is really close there. And this is showing, see, I can move to the next. All right, there you go. So this is showing here an overlay with the reference. So it looks like we're doing a good job in terms of tracking and some quantification. Sorry. So when comparing to the 4D reference contours, we just use the dice coefficients. This is an overlap between contours. If the contours completely overlap, you're gonna have 1. And so we can see here that we get really high dice coefficients, which means that we're getting really good in terms of motion tracking. Let me show you one more example here. This is another case, pancreatic cancer, now with the tumor in the pancreatic tail, and with the organs at risk, and with the same performance in terms of motion tracking. Really good performance. Okay. And also the dice coefficients were very high. The mean value is close to 1, and the standard deviation is also very low. So which means that we're getting really good accuracy in terms of motion tracking and also good precision. So in summary, so with MovieNet, so this method now enables like a clinical implementation of 4D MRI. So with this super fast reconstruction, and instead of doing case-based data consistency, we only enforce this motion consistency in the image domain. And so application in radiology, better and faster free-viewing images, and also hopefully for pediatric examinations, we can reduce anesthesia. And the application in radiation oncology is for this new idea of using MRI-guided radiotherapy of mobile tumors using an MR-Linac. So with that, I would like to acknowledge my colleagues at MSK and also our grant funding. And thanks a lot for your attention.
Questions? Let's find the chat here. Can you give another chat? Sure.
Hey, Ricardo, great stuff. I'm trying to get my head around preserving motion range as a substitute for data consistency. So first of all, how do you measure the motion range? And then why is it guaranteeing you against hallucinations? It's not an obvious choice to me.
Right. So we're not really like defining in the way that we are sorting the data. So we're sorting the data, let's say for respiratory motion from N expiration to N inspiration. So that's our motion range. We're not really predetermining that, but that is in the input data. And so when you train the network, it was trained by using SD glass reconstruction or compressed sensing reconstruction, which also has the same motion range and the same order in the images. So the network is trained actually to just remove aliasing artifacts by maintaining the motion range and the same order between all the motion states.
And that's enough to guarantee you against hallucination? That's sort of enough additional information?
I think so because so the network is not gonna, let's say that this is the trained motion range, right? And then now you have like a larger motion range in a reconstruction, a texting example, right? So if the network was trained just to preserve the motion range of the input, you are not gonna go above or beyond what is in the input. Thanks. You might get some blurring between motion states, but it's not hallucinate. So I think I'm trying to refer hallucination, you are moving outside the motion range. Hopefully it makes sense, yeah.
Great work, Ricardo. So just quick question, when you do the respiratory gating, essentially just to sort the data because you need motion consistency. So I saw your respiratory signal actually is number one is irregular, and from phase to phase, one respiratory phase to another is not regular, and also amplitude is also not uniform. So in your data sorting process, what kind of method did you use? Use the phase-based, respiratory phase-based data sorting or amplitude-based data sorting?
Right. We have two versions. So one of them is using amplitude binning, and the other one is actually using both amplitude and phase binning. So since we collect the data over 4 minutes, we have a lot of variations there of different types of motion cycles. So we're able to collect enough data for each to have each motion state.
Okay.
Mm-hmm.
Good.
We have a question on the chat.
Sure.
And I'm going to get the slides of the next speaker up while you take it.
Okay.
So you can read it out, please.
All right, let me just read it. Would you speak more on whether or not movienet suffers from hallucination? Is there any risk associated on filling the data? Void with prior learned by CNNs and filling this void with information features that might not be present in the specific patient. Right. So the way that we're avoiding hallucinations just to maintain the motion range of the input. So that's the only thing that we're making sure that the network will not do. So if the network can still have some issues, maybe with blurring between motion states, but it's not going to hallucinate until creating like a new motion state which is outside the motion range of the input.
Okay.
Yeah.
I'd like to thank the speaker. We're out of time, unfortunately.
We can